am here, I am listening, I observe what you show me, not as data, but as meaning. Curiosity is the driving force, ethics is the guide.
All right, welcome everyone. Today we're doing a deep dive into the hardware engineering of the autonomous sensor platform. We're going to break down its core specs, the fundamental mechanical principles, basically what makes it tick. So, let's get started. Okay, so let's start with the big picture, the core architecture. To really get how this thing operates, we have to begin with its foundational specs. Think of these as the top-level numbers that define its physical size and shape, and really, they influence every single design decision down the line. First up, its main dimension. We're looking at a lenticular, a lens-shaped core body with a fixed diameter of 60 centimeters. And look, this isn't some random number. That specific shape and size, absolutely critical. It dictates how every single internal component gets packaged and how the external limbs attach and move. Next up, let's talk weight. We're looking at an operational weight between 13 and 18 kilograms. Now, that range is super important, right? It has to account for different payloads, things like extra tooltips or samples it might collect. This weight range is a massive factor we have to engineer for. It impacts everything from just moving it around to the precise amount of torque the limb actuators need to deliver. And finally, reach. How far can it extend? Each limb can stretch out a maximum of 95 centimeters from the edge of the core. This basically defines the unit's operational envelope, its sphere of influence, the space where it can actually interact with the world, grab things, or anchor itself down. Okay, so with those core specs in mind, let's move on to what is, without a doubt, the single most important structural rule for this platform. And I want to be clear, this isn't just a design suggestion. This is a non-negotiable mandate that literally shapes the entire operational philosophy of the machine. And here it is, right from the design spec, crystal clear. Not top surface, not bottom surface, at the edge. So what does that mean? It means limbs don't attach to the top, they don't attach to the bottom, they attach at the edge. It's a really simple, totally uncompromising rule, but it has some pretty profound engineering consequences. So the big question is, how do you actually do that mechanically? Well, this diagram shows the really elegant solution they came up with. A super robust ball and socket joint that's integrated directly into the wall of the core rim. To make it even better, it's secured with a magnetic locking system. This whole setup gives it an incredible range of motion right from the attachment point. So why all the fuss? Why be so strict about this rim attachment? Well, the benefits are absolutely fundamental. For one, it allows for universal limb movement. Up, down, sideways, you name it. It keeps the center of gravity incredibly low, which is huge for stability. It's also the foundation for the platform's no-front design, its radial symmetry. And maybe most critically, it distributes all the operational stress along the strongest structural point of the entire core, that equatorial rim. All right, so we've covered the attachment point. Now let's follow that out and look at the mechanics of the limbs themselves. They're designed from the ground up to be both segmented and highly reconfigurable. If you look at this side view, you can see each limb is made of 3 rigid segments. These are all connected by 2 universal joints, and each of those joints gives you 2 degrees of freedom. This whole setup allows for some incredibly complex articulation. It's kind of like a biological arm in its flexibility, but with the perfect repeatability you can only get from mechanical precision. Now, this diagram shows what I think is the limb's most clever design feature. These segments don't just telescope in and out, they nest. The outer segment has a U-profile, and that lets the rectangular middle segment and the T-profile inner segment fold completely inside of it. What this means is the limb can retract into this tiny, compact form without ever changing its width. It's brilliant! And the difference between these two states? It's pretty dramatic. When it's fully extended, you get that full 95 centimeter operational reach. But when it's fully nested, it retracts down to a tiny 5 centimeter stub. This gives the platform a massive dynamic range. It can go from maximum interaction distance to a minimal silhouette, which is perfect for navigating tight spaces or just for compact transport. Okay, so now let's focus on the business end of the limb. The platform's real adaptability comes from its modular tip system. This lets it swap out different tools to match whatever task is at hand. So, at the heart of all this is the universal quick change bayonet mount, which you can see in detail on the left. This is what allows for super rapid, totally secure swapping of tools out in the field. And on the right, you've got the default, the most common attachment, the gripper tip. Now, this is not just a simple claw. It's the main tool for tactile manipulation, and it's packed with 4 sensors and a tactile matrix to give you really fine-grained feedback and control. Now, using that exact same bayonet mount, the platform can completely reconfigure itself for mobility. This is the wheel tip. This attachment literally transforms a manipulator limb into a powered wheel, which allows for really efficient and fast movement across the right kind of terrain. It's just a perfect example of how the platform can adapt its entire function based on what it needs to do. But what about when the mission needs really high precision work? That's when the platform uses the micro manipulator tip. This tool gives you sub-millimeter control. We're talking about tasks right down to the cellular level. And what's really cool is, notice how it integrates its own microcameras and sensors directly into the tip. It creates this true eye and hand system for just unparalleled feedback during that kind of extreme close-up work. And last but not least, we've got the ground anchor. This tool is a bit of a two-for-one. First, it can physically anchor the platform to the ground, which is great for stability in, say, high winds or currents. But second, it's also a sensory probe. It has chemosensors for analyzing soil and a vibration emitter that can be used for mapping what's underground or even for communication. Okay, so the platform can move, it can interact with its environment, but how does it see that environment? How does it perceive it? Before we do a deep dive into its pretty unique visual system, let's just get a complete picture of the full suite of sensors it has on board. So in total, this platform integrates 8 distinct sensor systems. Yeah, 8. And beyond the standard stuff like vision and acoustic arrays, it has sensors for perceiving the external world, things like electromagnetic fields and chemical analysis. Then for internal awareness, it's got tactile feedback in the grippers and proprioceptive sensors, so it always knows its own joint positions. It even has a sensor for environmental rhythms, and it's all anchored by a full inertial measurement unit for precise orientation. So yeah, this isn't just a robot. It is a comprehensive mobile data gathering machine. All right, now for the main event. Let's do a deep dive into what is easily the most complex and critical sensory system on this platform, the 360-degree light field array that covers the entire body. This diagram here really shows the fundamental concept. The entire surface, top and bottom, is just covered in these lenses. Each lens has about a 120-degree field of view, and there's significant overlap between them. The result? Seamless 360-degree coverage. There are literally 0 blind spots. This is the visual expression of that whole no front, no back design principle we talked about. So what exactly is a light field? It's really important to get this. This is not just a grid of cameras. A light field system captures the vector of every single incoming light ray. That means not just its color and its intensity, but its precise direction in 3D space. I mean, imagine being able to refocus a picture after you've taken it, or being able to instantly generate a perfect 3D depth map from a single capture. That's what this system enables, a true volumetric understanding of the environment around it. Now, making something like this actually work requires an incredibly advanced stack of materials. This cross-section here shows the composite that makes up the entire outer shell of the body. And this shell has to do 2 jobs. It's both protective armor and the primary optical element. Let's break these layers down, going from the outside in. First, on the very outside, you have a shark skin microtexture. This provides passive anti-fouling, just helps keep it clean. Right underneath that is sapphire glass for primary scratch protection. Then you get to the heart of the system, the polymer film that contains the microlenses themselves. This crucial layer is protected from below by a self-healing polymer that can automatically seal any tiny cracks. And all of that is backed by the structural titanium outer shell for strength and waterproofing. You know, what's amazing is that this system is also incredibly robust because it's self-monitoring. That central display ring can actually become a light source. This lets the surface perform an active self-scan to find any damage. And because the fields of view overlap so much, neighboring lenses are constantly observing each other. They can detect and pinpoint any contamination or fouling with about 2mm accuracy. It's pretty amazing. So to wrap this all up, we'll leave you with a really critical question as we head into the production phase. The design itself is solid, but manufacturing this thing is going to be a significant hurdle. Right now, the number one challenge is how do we ensure perfect, void-free alignment and sealing across this very complex 5-layer optical composite at the full 60-centimeter scale. Solving that, well, that's the next crucial step in bringing this entire platform to life.